All right. So the bipartite graph. Uh, so the idea of bipartite graph is a graph. So let me just go straight to the definition. All right. So here's bipartite graph. Bipartite graph is a graph that can be partitioned into two parts, such that the two parts meaning two non-empty parts. So it's really uh, two parts with at least one node in each of the part. Now, the parts have to satisfy the following requirement in that every edge on the graph must connect from one part to the other part, not within the same part, all right? Not within the same partition. So it's bipartite graph if you can essentially partition the graph that way. Now, in particular, also the graph cannot contain loops because loops connect one node to itself. That means it connects uh, nodes in the same partition. So we don't want that in bipartite graph. So now with that definition, so let me go back to this. So we are looking at different possibilities for bipartite graph, right? So can we enlarge this? Nope. Maybe only this one. So, all right. So let me start with this. Um, so, so this question is a combination of different concepts in the lectures, in the video lectures. So, first of all, the first one is pretty easy. So you want to determine whether this is a bipartite or not. So how do you determine if the graph is bipartite? Well, the way you do it is you start with a node and then place a marking on each of the node alternately. So with colors, for example, alternately. So for example, let's start with red. Let's use color red and blue, right? So let's start from, I don't know, let's start from R. Let's start from the node F. So you give a color, well, you give a label R, meaning red. And then all neighbors of F should be given color, the other color. So for example, blue here, or let's call it green, all right, green. This is green, and this is green. Now, here, what we do is we color the graph completely until we get no violation, or if we get a violation in that two nodes that are adjacent to each other, if they have the same color, then it's a violation. So in this case, this is a violation. It's a violation, all right? Why? Because B and E are colored with green, and B and E are adjacent. So it's not a bipartite graph. All right, that's the first one. Any question? No? No, if not, then let's have a look at the second question. So the question is, what is the graph obtained by performing edge contraction on the nodes B and F in the graph here gives is a bipartite, right? Is it a bipartite after you contract the HBF? Now, so what is the contraction? Contract BNF. So contract BNF means that, well, you essentially you take out the edge. So let me use a different color in this case. Let's use red. We take out the edge, yeah, and then we create a new node, say call it W, and then for each node neighboring to, so we remove the edge and we merge B and F into W essentially, right? So what we do is essentially in a formal way, what we do is we remove B, we remove F, we put W here, and then we give an edge to W from every neighbors of B or F. So that means you go this way. Yeah. So you go this way. So you go this, where's neighbor of, right? So this way, and that's it. Yeah. So what we get is something like A, W, C, and then D, all right, and then E. So A goes to W, C goes to W, and then A goes to D, C to D, and then C to E, A to E. Yeah. All right. So now, is this graph bipartite? Anybody?
It is, sir.
It is bipartite. Yes, that is correct. So it is easy to see. For example, let's start with green here. Green or green and then blue and then blue. And then, all neighbors of A must be green and green. So it's all neighbors of C, right? So yes, so it is bipartite. So there's no violation. So, and this one is bipartite. So remember, there is no double edge, right? So in this case, yeah. So although you have B as neighbor C and F, and then A as an sorry, F as a neighbor C, and B, so and sorry, neighbor of B is A and C, neighbor of A F is C. So we merge F and B when we rename it W, and well, the H. So we don't have a double edge, for example, because you have B, C, and FC. It doesn't mean that we get two edges here. But there is a in the graph theory, sometimes people use a slightly different definition of contraction. So in this case, for example, instead of WC a single edge, because B is a neighbor of C and F is a neighbor of C, so you get two edges like this from W to C. But in this case, we follow the convention that, well, we don't introduce double or parallel edges, right? So yes, it is bipartite, right?
Sir, can I ask a question
Yes,
again?
sure.
If it's in that case, if there is a parallel node between one of the um, between B and F, let's say, will it become a loop or will it just disappear, sir?
That's very good questions. Now, here's the tricky part. So when I say performing edge contraction on this edge, this implicitly says that we only have one edge, all right? But it will be different, as you said. For example, if we have something like this, A, and then B, and then C, and then D. So suppose you have A like this, parallel edge, right? That's what your question, right?
Yes, sir.
So you want to contract an edge between A and B. Now, in this case, if we have parallel edge, we have to mention, we have to we have to we have to we have to pinpoint exactly which edge are we talking about. So in particular, in this case, we will probably give a name for the edge. For example, let's call it E1, E2, E3, E4, and E5, right? So then the question is whether you want to contract E1 or you want to contract E2, all right? And then in that case, the other edge becomes a loop. Yeah, I think it should be that way. Yeah. Let me do a double check because the examples in the, I think, do we have an example where we do have a loop? No, not this one. I think you will get a loop in that case. Let's see. Uh, 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 the book has examples 19. Examples 19, which is so example 19, yes. Figure 16. Yes. Right. So yeah, we don't have an example that way. Mm, yes, I think it should be a loop because because when you contract an edge, you don't remove other edges except that one edge,
But
right?
since in this case it's only one edge, we can just directly remove it, sir.
Uh,
In
so
this case,
which one?
the pre-class quiz case, sir.
The pre-class quiz case, we don't remove an edge there. We don't remove an edge, but or your question is because we so the way we do it is this way, right? So maybe a better way just to do it this way, right? So first, the set. So so you have a set of vertices like this, right? A, B, C, D, E, F. Now the E and F is removed, yeah. So you remove E and F, and then you union say W, right? And then the edge becomes uh, the new edge, yeah, becomes the original edge minus the edge E and F, sorry, B and F, right? Okay. Yeah, and then plus all edges. Let's call it P, such that uh, let's call it not P, but rather let's call it W X, where X is neighbor. Hold on a second. A neighbor of 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 B and F. So yes. So in that case, I think you got a point here. So let me put a, because there might be two different opinions in this case. Uh, the examples in the book does not or do not indicate what happened if we have contraction. Mm, mm, mm. Uh, let's check. Um, I don't think we have an example. Uh, let's put that question in mind. I'll try to find out the strongest statement on that. If we have a case where we have parallel edges, um, and go back to that once I got the answer right now. So I don't have a clear answer on that. Um, mm, yeah, we don't have an example to that. Let me hold on a second, step back a little bit. Because I believe there are different views on that. Uh, so it's okay. There is a definition in Wikipedia. So let's go back to that after the break, right? And go back to the question. Yeah. Uh, so let's go back to that and then investigate whether the correct answer should be having a loop or not. All right. Good. Uh, so let me go back to this lecture. This is a bipartite graph. The next part is graph G, whether, so let me shift this down a little bit. Now, this graph G is so if you draw this graph, should be pretty easy to see that if you have A, B, C, D, and E, C, D, and E, and you have an edge between A and B, and then A and D, and then C and B, and then C and D, and D and E. So, is this bipartite or not? The answer is
Yes, sir.
yes, it is bipartite, right? So let's color it with black, white, white, and this is black, and this is white. Yeah. So that's for example, right? So, what about this one? Induced subgraph of graph with respect to that ABEF. So what is an induced subgraph? An induced subgraph is defined in the subgraph operation. So a subgraph is really just a graph whose vertices and edges are subset of that original graph, right? So you simply take the subset operation on that on that original graph. Yeah. Now there is also the notion of induced subgraph of G with respect to W is a subgraph G whose nodes are in W and edges are those from E that connects only pairs of nodes in W. That means really we limit the graph only to a few nodes. So in this case, for example, what is the induced subgraph? Induced subgraph with respect to A, B, E, and F is this graph, right? So you take out you only take A, B, E, and F. So you have A, you have B, you have E, and you have F. So you have A and B. There is no other edge between A to E and F. So what about B? We do have B, E, B, F, and that's it. So this is the induced subgraph. Now this is obviously bipartite, right? Because, well, you could color so B is one partition and A and F is in the other partition. So the bipartite subgraph gives us B and also A, E, F. Yeah, so this is the partition. Yeah, so yes. And then union of these two graphs is this graph. So A, B, C, D, and then you have E, F, G, H. So let's put it this way. So you have A, B, A, C, A, D, B, C, B, D. And then you have A, E, A, H, AF, and then EH, no, GH, and then you have FG. Now, is this graph bipartite? Well, we can simply check, right? So let's start from, say, A. Let's color it with green. So that means the all other neighbors have to be red. So this is red, red, and red, and this is red, and this is red, and this is red, and this is green. So yes, this is a bipartite graph. All right. Any question?
I don't think it is bipartite, sir, because in that case, C and B both have
You're
the
right.
same color.
B and D, I should say. Yeah.
Yeah.
Right. So not bipartite. Sorry. Good point. So not bipartite. Why am I looking at wrongly? Sorry about that. Yeah, it should not bipartite. So let me erase that. Yeah. Good. All right. So that's first question. So let's move on to the next question. Question 2. All right. So for question 2, we're looking at this graph. Now we're looking at matching. Now this time we look at matching. What is matching? Here it is. This definition of matching. A matching is a subset of edges such that no two edges are incident in at the same node. So look at this, right? No two edges are incident at the same node. Oh, something is. One second. Oh. All right. So no two edges in the subset are incident at the same node. So first of all, remember that matching is a set of edges, specifically a subset of the edges of the graph. So you pick the edges, not picking the vertices, not picking the nodes, but picking the edges. And then you pick the edges such that no two edges are incident in the same at the same node. So here's an example. The red edges are the matching, but we have different kinds of matching. In this case, a perfect matching on the upper left here. This is perfect matching because the matching involves every node. So all nodes are paired to another. Each node is paired to another node. Yeah. So that's a matching. Perfect and maximum matching. Yeah. Perfect has to be maximum in this case, right? So is the bottom left. All right. But on the upper right here, we have so let me put it here. So the HR AF, or let me write down like this. So AF and then DF, I should say DF, AB, GH, and CE. Yeah. Now, how about this one? This one has a matching BD, EH, and then GF. Yeah. So that's a matching. So for example, in this matching on upper right, you cannot add GE or nor can you add GH. So you cannot add GH or you cannot add GE, because if you add them, then you will have two edges incident at the same node in this particular node, namely G. Right? So it's maximal. It's called maximal because you can no longer add one edge to the matching without breaking down the matching. So, for example, if you add A, B, then you break down matching because the matching is no longer a matching. So is, for example, this node, this graph, right? So you have matching involving B, D, and GE, and no longer can you add another edge to that matching. So that's why it's called maximal. So you can have more than one maximal matchings in one graph of different size, and the matchings may be of different sizes. All right. So that's the principle. So let's go back to this. Is this a maximal matching?
It is, sir.
So let's color that, right? So where is my pen? So it's green now. So we have AG. So this is our matching, and then we have BF, and we have DE. Right? So that's a matching, obviously. Now, can we add another edge? You cannot add AF, AE, GD because you will violate that. You cannot add AC because then you will violate the matching condition. And then you cannot add, for example, CD, right? Because you will violate the matching condition. So that is a maximum matching. So this is true. Small pen. True. All right. Does G have a perfect matching?
No, sir.
Why?
Does not. Because in this case, if we can actually create the adjacent list, C is connected to ABD, and then so is E, F, and G is connected to AD. In that case, the only way we can put C, E, F, and G is by those three nodes, right, sir? But
Yes.
then by the pigeonhole principle, for instance, G will then violate the matching principle, sir.
Yes, that is true. Or there is an easier way, or maybe not. Let's have a look. A matching is perfect if all nodes are matched, right? Now, and then together with the definition that matching consists of edges that are not incident at the same node, that means they don't share the same node, right? So that means the number of nodes in a complete matching, sorry, a perfect matching, number of nodes in a perfect matching must be even, right? So here we don't have an even number of nodes. Yeah, we have seven nodes, so it's not, cannot be perfect. So no. G has a maximum matching of size 3. Well, we do have this one, right? This is size 3. Can we have something bigger? Can we have a size 4? Let me draw it here. A, B, C, D, E, F, G. All right. So, and there is an H here. A, G, A, F, A, E, and A, C. And then B, F, B, E, then B, C, and then B, C, B, E, B, F. Okay. C, A, C, D. D, G, and then D, E, E, A, E, B, E, D, F. Oh, there is another one. D, F. All right. Can we have a matching of size 4? If we have a matching of size 4, then we need how many nodes? Anybody? If we want to have
8,
matching,
sir.
8, correct. But we, how many nodes do we have?
7, sir.
So there cannot be. So that means first, there cannot be a matching of size 4 or more. Yeah, because of the number of nodes are only 7, right? Because the number of nodes are is only 7. And then now let's have a look at matching of size 3. Is there a matching of size 3? Well, the answer is yes, right? Namely, for example, the graph in, sorry, the matching X, yeah, the matching X. So it's a yes, right? Any question? No. If not, then let me go to question number 3. Again, this time. So let's throw it here. So A, B, and D, F. A, B, and D, F. Is this a maximum matching?
It's not, sir.
Okay. What do you suggest?
There is another one that has 3 elements, I believe. A, F, B, E, and C, D, for example. Sir.
A, F, B, E, and C, D. Now let's have a look at the definition of maximum matching. Now be careful here. A maximum matching. So let's make sure, right? So matching maximum if the size is greater than or equal to the size of other matching. So here, if you look at this, we only look at the size of the matching, not really look at the structure of the matching. So this is different from, for example, when what we learned in in the topic of relation, when we talk about maximal element or minimal element of partial order, we look at the position or where the elements in the ordering, right? But here we only look at the size, yeah. So because we only look at the size, so yes, then it is not maximum matching, not maximum matching, because there is a matching of size 3, right? Yeah, namely A, F, B, B, E, C, D. G has a perfect matching. Do we have a perfect matching?
Yes, sir.
Yes. What are they?
That one, A, F, B, E, C, D.
Correct. So A, F, B, E, C, D. Yeah. Or if you write it like this. All right. Yeah. Does G have a complete matching?
No,
What is
sir,
a
because it's not a bipartite graph.
right? So uh, a complete matching from a node to another node, from a set of node to a set of other nodes in bipartite graph. So the bipartition. So matching complete means that you go from one partition to another partition such that every node in the origin is matched to some node uh, in the uh, in the destination. So, but here in this case, this is not a bipartite graph. Yeah. Yeah. So that means we don't consider bipartite matching, sorry, complete matching uh, uh, if it's not a bipartite graph. So no. Yeah. Because G is not bipartite. All right. Good. Uh, question number 4. Let's look at this. Now we look at the adjacency matrix of this. What is the adjacency matrix of this? Well, S1 to S6, so there is a 1 here. Oops, sorry. There is a 1 here. And then S1 to S4 and S5. So 1 here, 1 here. Yeah. And then S2 to S4, S5, and S6. So again. And then S3 is from, so I forgot S1 to S3 as well. S3, S4, S5, S6, yes. Now, S3 goes to S6. And then S4 goes to S5 and 6. And finally, S5 doesn't go anywhere. So is S6, right? So the rest are 0 in this case. Yeah. So that's adjacency matrix. What about the incidence matrix? Uh, let's have a look at the definition of incident matrix, just to be sure. Now, what is incident matrix? So adjacency is um, if so, this definition allows us to cover also parallel edges. But if we don't, if we have parallel edges, then we need to use this definition, um, like this one. So, what is the incidence matrix? So here, the matrix is um, contains the degree of the value of dij, where dij is 2 if the edge is a loop at that node, and 1 if it's not a loop but incident at pi. Now, what about directed graph? Here in directed graph, we put 1 and minus 1. Yeah, so that means here, yeah, what we do is, so we have, so for example, E1 is the edge between S1 and S6. So S1 and S6. So S1 goes from S1 and S6 is minus 1. Minus 1. Yeah. So just to be sure, like that, right? So the target gets a minus 1 there. Now, what about E2? E2 is an edge between S3 and S6. So from S3 to S6. So that means here S3, S6 is minus 1. E3 is from S1 to S3. E4 is between S1 to S5. Sorry about that. I mean minus 1. Here has to be minus 1. And then E5 is between S1 and S4. So E5, S1, and S4. E6 is from S4 to S6. S4 to S6. And then E7 is from S2 to S6. E8 is from S4 to S5. So yes, like this. And E9 is from S2 to S4, and S2 S5 is for E10. So there's 4, S2 to S4, and then S2 to S5. Yeah, so that's how we define the incidence matrix. Any question? The rest are 0, right? And notice that the columns are all summed to 1. So the columns, the sum of the, sorry, not 1, but 0. Yeah, the sum of the columns has to be 0 for directed graph. Good. Now, how about question number 5? So let me pause for a second. We are given these two graphs. Let me enlarge this. And you want to determine whether these two graphs are isomorphic or not. So let's go through the questions. So first of all, this should be easy, right? So how many vertices do we have for G? We have 8, right? And how many edges? Oh, 1, 2, 3, 4, 8, 10, right? What about H? H, you have 8 vertices again, and edges, you have 10 edges. So both graphs have the same number of vertices and the same number of edges. Now, how about the degree? So that means because they have, so okay, the idea is that the idea is this, right? So two graphs are isomorphic if they are of the same form or the same shape. Yeah, you can make them the same shape, yeah, or the same structure, ignoring the names of the vertices, right, and the edges. So to determine whether two graphs are isomorphic or not, what you could do is you find out if there is any invariant properties violated, then the graphs are not isomorphic. So for example, if the graphs have no, or both graphs don't have the same number of edges or don't have the same number of vertices, then they cannot be isomorphic. Yeah, they cannot be isomorphic. So now, because they have the same, they may be isomorphic, but maybe not, right? Because we have to check other properties. So let's have a look at the degrees. What are the degrees of U1? U1's degree is, well, let's fill this out, right? Or let me just copy this and then paste here. All right, so here, right? So what is the degree of U1? U1 is 3, U2 is
3 also, sir.
3, U3 is 2, U4 is 2, U5 is 3, U6 is 3, U7 is 2, U8 is 2. Now, and then degree of V1, 3, V2 is 2, V3 is 3, V2 is V4 is 2, V5 is 3, V6 is 2, V7 is 3, V8 is 2. So G has how many vertices with two with 2 degree with degree 2?
4, sir.
4. And we have 4 degrees, 4 vertices of degree 2, 3, right? Yeah. 1, 2, 3. Okay. So H has how many vertices of degree 3? Of degree 2, I should say.
Also 4, sir.
1, 2, 3, 4. And 4 vertices with degree 3, right? Okay. Have the same. I think the question is a mistake here. Same number of vertices with the same degree. Okay, but then my question is this graph isomorphic or not?
Yes, it should be with the same degree.
Okay, but hold on a second. So give me the mapping. For example, U1 is mapped to what? So remember, an isomorphic graph, two graphs are isomorphic if you can map one to the other. All right. So let's have a look at the definition here. Um, uh, Here. So if you can redraw one graph to the other, then essentially the graphs are isomorphic. So you have to make sure you have a mapping, you have a function from one graph to the other. All right. So let's just look at this example. So here, for example, you can try mapping, for example, C to U, right? C can be mapped to U. But if C is mapped to U, because this is of degree 3, this is of degree 3, this is of degree 2, this is of degree 2, yeah, so 3, 3, 2, and 2, yeah. So if C is mapped to U, then what happens is that all neighbors of U, so all neighbors of C must be mapped appropriately to neighbors of U, right? So in this case, neighbors of C is, what is it? A, B, and D, right? So A must be mapped to what? B must be mapped to, well, the only degree 3 is W, right? So how about B? Now, to make sure that we do it correctly, then we have to look at the edges, right? So, if can we map, so suppose we map A to B, then the edge AC or CA must be mapped to UV, right? Yeah, so that's good. And then you have CB must be mapped to UW, which is fine, so there is no problem. And then CD must be mapped to then to X, yeah, UX. Now we have to check other edges as well. What about, so we have AC, we have AC, BC, and CD, yeah. So we still have BB and AB, right? So we're AB. AB has to be mapped to VW. Do we have VW? Yes, we do, right? So here, yeah. And then BD has to be mapped to WX. Do we have WX? So this is BD, this is AB, and this is, of course, UV is AC, U, BC, and then CD. So yeah, so in this case, there is isomorphism. But how about this one? Look at this one. We have, so, right, so in this case, it doesn't have a isomorphism. Let's have a look at some more examples. So the one above, we have 5 vertices and 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8 edges. 1, 2, 3, 4, 5, 6, 7, 8 edges. So now let's have a look at this. Does these two graphs have are these two graphs isomorphic? What do you guys think? Let's have a look, right? So we know that the only, no, it's not, right, because here we have a vertex with degree 4, but here we don't have that, right? Oh, we do. So we have one. So C and this is degree 4. So C and E have degree 4. So this is 4 and this is 4. This is 3, this is 3, this is 2, and this is 3, and this is 2. This is 3. So the only way to make it isomorphic, to make them isomorphic, is mapping D to phi, right? So D is mapped to phi. And then what are the neighbors of D and they are C and E. So C, E, and C is of degree 4 and E is of degree 4. So then in this case, let's simply choose U and W. Yeah. And then CD is mapped to UV, and then CDE is mapped to VW. Yeah. Now, what about neighbors of C and neighbors of E? Well, we have CE as an edge, and therefore UW is an edge as well. Must be an edge in the other graph, right? So we are done with this, with this, with this. Yeah. Now, the next is from C, you have an edge to A and B as well. So Y and X can be A and B. So here in this case, A maybe is Y. So, and therefore AC is uh, as uy, and then uh, b is x, so therefore uh, bc is ux, yeah, so uy and then ux, so we're done. And finally be and ae, so this is be, so it has to be, so you have to check be is wx, which we have, and then and then ae has to be ux, which we have already. Hold on a second. Ae has to be xy, xwi, sorry, wy, and then finally ab has to be xy, right? So we're done, right? Now, how about the one below? Here, the one below, you have, this is of degree 2, 2, 2, and 3, and 3. Here we have 3, we have 3, we have 2, we have 2, we have 2. Are they isomorphic? So this is a yes here. This one, well, let's check, right? So can we try mapping a correct node? So for example, here, the node U and W are of degree 3, have degree 3, so A and B have degree 3. So let maybe map A to U and B to W, right? So that's the only way, right? But here we have an edge. Hold on a second. So here we have, and then we have an edge to E is of, so we have an edge to A to E, and B to E. So E must be phi, right? So therefore the edge must be U phi. So U phi, and BE must be PW, right? And then there is an edge, so we have A to D and C. So now let's check here. What do we map D to? So D has to be of degree 2, right? So maybe Y is the choice. Now C has degree 2, but how do we map C? Do we map it to W? No, right? So this is not isomorphic. So here, be careful. Although the degrees are the same, so you have the same number of vertices of degree 3 and same number of vertices of degree 2, they may not necessarily be isomorphic, all right? So you have to be careful, making sure that there are the mappings, the actual mappings for isomorphism exist, right? So now let's go back to this question. So I think we cannot just say this, yeah. So let's strike this out. We have to make sure first that the mappings are correct. So in this case, maybe we could try U1, and U1 is of degree 3, right? So this is of degree 3, and this is 3, this is 2, this is 2. P1 is of degree 3, and this is degree 2, and this is degree 3. So what is our choice? So let's have it here. So degree 3, 3, 2 and 2. This is 3 and 2 and 3 and 2. So U1 has choices to which one? What do you choose for U1? Is it phi1 or phi3 or phi5 or phi7? What do you want to choose?
You want, sir?
Let's choose phi1, right? Let's try phi1. So if u1 is phi1, then the neighbors of u1 is u2 and u4 and u5, right? u2, u4, and u5. Of them, u4 and u5. Of them, of these three, the only one with degree 2 is u4, right? So which node is on degree phi, the neighbor of phi1 that has degree 2?
V2, sir.
Phi2. Why not phi4?
With V, oh, it's a possibility as well.
Well, so you can try u2 to phi2, then u4 has to be mapped to maybe so u4 has to map to be phi2, right? And then u2 has to be mapped to either phi3 or phi4, right? But u2 has degree 3, right? So it has to be mapped to phi3, right? But then u5 having degree 3 has to be mapped to
V5, sir.
u5 has to be mapped to phi5, and then sorry, no, this is phi4, right? Phi4. All right. Phi4 or phi2? Sorry, I'm confusing myself. Let me redo this again. So let's erase this. So the degree of u1 is 3. So we're looking at uh, u1 here and looking at degree 3 in the other graph. So u1 is all matching. So what about u2, u5, and u4? Now looking at u4 has only degree 2, and the neighbors of of phi1 with degree 2 is phi2, right? Or phi4. So maybe we choose phi2. Sorry, phi2 here. Now, in that case, so we're done with u4 and u1. Oh, but u2, u2 is of degree 3, and we only have phi5 of degree 3. And then finally, u5 is of degree 3, but can we map u5 to phi4?
No, we can't, sir.
No, we can't, right? So our matching is wrong here in this case, or pairing is wrong. So maybe choosing phi1 is not correct for u1. All right, so let's do that again. So u1. Now let's try mapping to another node. Let's use phi3, right? Yeah, u1 has phi3. So what we have u2, u4, and u5. The only node degree uh, with degree 2 is u4, and the only neighbor of phi3 with degree 2 is, well, in this case again we have phi2 or phi4, 5, right? So maybe we try phi2. Oh, by the way, here even if we choose phi1, but here we choose phi4, then here again phi2, right? You cannot have it, right? So therefore, only choice here is that, so again, so u4 u4 has to be mapped to well, maybe phi2, right? Now again, the neighbor of u1 of degree 3 is u5 and u2, so u2 of degree 3, so therefore here must be phi7, and again P5, U5 has to be mapped to P4, which is not possible, right? Now, how about our choice? Let's say instead of P7, let's choose a instead of P2, let's choose P4, right? And then in that case, U5 has to be mapped to P2. Yeah. So again, not possible, right? So we can choose P3. What about choosing P5? Yeah. So U1 to P5. Yeah. Then you have U2, U4, and U5. Here in this case, between P5, then the neighbor with degree 2 of U5 is only U8, right? So sorry, U1. So neighbor of P5, the degree 2 is P8 or P6, right? So in this case, you could use P6 here. So what about U2? U2 is of degree 3, so it has to be mapped to P1. And then therefore this has to be mapped to P8, right? Which is not possible again. So you could try it again, and eventually you cannot find the correct mapping. All right. So why? Because, for example, U1 has two neighbors with degree 3 and one neighbor with degree 2, right? Now, in the other graph, do we have a vertex or a node with this property? Is there a node in graph H such that with degree 2, U1 has degree 2, has degree 3, sorry, degree 3, with degree 3, and having those neighbors? No, right? Yeah. But all nodes in H with degree 2, sorry, with degree 3, yeah, have one neighbor with degree 3 and two neighbors with degree 2. So the answer is not isomorphic. So the answer should be not isomorphic. Any question?
So, sir, to ensure, well, to check if it is possible to have isomorphic structure, the only way is to brute force. Say, is that the only way, sir?
Essentially, yes.
Okay, then.
So there is no shortcut, unfortunately. Maybe later on, if you learn algorithm theory of algorithm design, analysis of algorithm, you will learn the notation, Biko notation. Have you heard about Biko notation, right? You've heard about it before. So the problem of finding an isomorphism between two graphs is an example of NP complete problem, meaning that that problem is formally it means that you can only use non-deterministic machine to decide this in polynomial time. Or in layman terms, that means that until now, there is no better algorithm than exponential algorithm, essentially. So, so, it is very difficult in practice, at least. Yeah. So we don't know yet. Yeah. So for now, yes, it's brute force. Unfortunately, there is a well. You could use some heuristics, right? For example, when we look at the graphs, try to map the so in the graph you can find nodes of degree 1, 2, 3, and 4, and so on, right? So try to map the nodes with the smaller possibilities. So for example, if the origin graph only has one node with degree 2, then you should start with that node, right? Because you only have one choice in G, then in H, if there is only one choice, then you're good, right? If you have two choices, is the least possible, the least number of possibilities, then two choices in G must correspond to two choices in H, right? So start with that, with the simplest, well, with the smaller number of possibilities first. But yes, in general, there is no, at least, more practical way than brute force.
Okay, thank you, sir.
Good question. Yes. So let's move on to Q6. So again, this is now this time we look at connectivity. This is a directed graph. Now if we want to ignore so let's use this. All right. Now, okay. So let's work on this. If we ignore the direction of edges, then then the question is there is or there is not, right? The answer, the answer choices are yeah, there is a or there is no, right? So A to B, yes, right? Let me give a check mark, right? A to C, can we go from A to C if we ignore the direction?
Yes, we can, sir.
Yes. A to D, yes. A to E, yes. A to F is yes. So it's B to C and so on. So essentially, if we ignore the direction, everything is connected, right? So because the directed graph, in the directed graph, there is a path between each pair of vertices. If we ignore the direction of its edges, then we say that G is weakly connected. Right? Now, what about this? Now, we want to determine if the graph is strongly connected. Now, in this case, looking at the direction, there is a path from A to B, yes. A to C, no. Yeah. A to D, no. A to E, no. A to F, yes. B to C, no. B to D, no. B to E is no. B to F, no. C to D is no. C to E, no. C to F, no. D to E, no. D to F, no. E to F, sorry. E to F is no. And then B to A, no. C to A, no. D to A, no. E to A, no. F to A, no. C to B, no. D to B, no. E to B, yes. F to B, yes. D to C, yes. E to C, yes. F to C, no. E to D, no. F to D, no. And then F to E is no. Right. So, is the graph strongly connected? What will be your answer?
No, sir.
No. Yes, it's no. Why? By this answer, right? So let me open this up. So here, uh, uh, if for every two nodes, there is a path from A to B and B to A, right? So it has to be both directions. So therefore, it's a no. It's not strongly connected. Yeah. Okay. Yeah, there is a pair of vertices. There is a pair of vertices U and P and G, such that there is not a path from U to V. What will be the choice answer here?
It does not have the one, sir.
Does not have. Oh, does not have, right? Yeah, does not have, sorry. Yeah, from U to V and V to U, right? All right, so that will be exercise, a pre-class exercise.
Sir,
Yes.
may I ask, is that supposed to be an N or is that supposed to be an OR? Because in the answer given, it's an OR, sir.
Hold on a second. Do I make mistakes? Strongly connected. Uh, 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 uh. N should be an N. So
Yes, sir.
this was
So
the answer. Was the answer an or?
yes,
Yes,
sir, it's
sir.
an or, sir, in the pre-class,
Okay.
sir.
Okay. I'll make sure to take note that. By the way, for the previous question, is the answer isomorphic?
The one, sir, I think it is only said, is it possible or is it not possible, sir?
Oh, okay. Then it is possible, right? It is possible, right? It is possible.
Yeah, yes, sir.
At that point, yeah. So this is okay. Although we then go deeper, right? So we actually determine that they are not isomorphic. Yeah. Okay. Good. Yeah. Good. So we have about 45 minutes left, but in any case, let's just take a break for about uh, 5 or so minutes. And I'll let me check your question, right, about edge contraction. Um, all right, so let's have a break for a short break. I'll come back. All right, so back to the questions on edge contraction. Just this one, not this one. Oh, the first one was it? Yeah. So contraction. So two types of contraction. There are two types of contraction in graph theory. So one always yields a simple graph, and two may yield a multigraph. So
Excuse me, sir. Excuse me, sir.
yes.
Are you sharing your screen, sir?
Oh, I'm sorry about that. So let me just share here. Here is what I just wrote. So do you see my screen now?
Yes, we can.
Okay, so here is the piece that I just wrote. There are two types of contraction in graph theory. One always yields a simple graph, and second alternative, or the alternative is may yield a multigraph. So in the case of one, then you cannot have loops. All right. So that means if you have this, like this, and then say you have this, A, B, and C, then after contraction, you get something like A, B, C, like that. Contracting, say E1. So let me just make sure. So formally, yes. Okay. So this is in the first one. I think the one we use in the textbook from Rosen is the first definition, right? Now, if in the second definition, then you may have parallel edges. You may have, so for example, this one. Say you have this, say A, B, and C, call it E1, E2, E3, and E4. If we contract E2, then you get this. So AB, and then C, and you have like this, and you have this. So this is E4, E3, and then E1, something like that. Yeah. If definition 2, right? If we use this definition, which one do we use? Well, in our case, in this class, for because we follow the textbook, in this case we chose the first one, but be mindful that there is another version, or they actually define two types, right? So with there are two types of age contraction. I hope that answers the question.
Yes. Okay, sir. Thank you, sir.
Okay, great. So now, because we only have like 30 minutes, let me recap some of the things that we talked about. I think we have I think we talked about that. Where is here? Subgraph operation. So let me just go through the concepts here. So subgraph and induced subgraph is clear. Yeah. I think I have the videos of this, so it should be quite obvious to do it. Also, edge addition and edge removal should be obvious. Vertex addition or not removal is also easy. Yeah. Remember, if you remove a vertex or a node, then the corresponding edge to that node will be gone as well. Yeah. Yeah. All right. Edge contraction. So here is another example. If we use first definition, so here's always a simple graph. Then the result would be, contracting E7 would be R QU, right? And then from QU to P and to P, like that. Yeah, if you always use a simple graph. On definition 2, I think in my video I used definition 2. I don't remember exactly because I created that last year. But anyway, you might want to take a look, right? So if with definition 2, so may yield multigraph. Then you get is something like R, you have QU, So here you have two edges like this. So here's your E3, E4, and then here you have a loop, E6. Then you have an edge, E2, an edge, E5, here E1, P and P. Yeah. So yeah. So that's an example, right? So just to be mindful here, right? So here in this case, well, this we could use E1, E2, and E5, but then here we have to use another name, E8, for example. Yeah. All right. Any questions on edge contraction? Hopefully not a problem, right? So this one is okay. We do have bipartite graph, which we talked about already. So just to be Clear, right? So we have a perfect matching if all nodes are matched. So remember, matching is simply a set of pairs of nodes or a set of edges. Yeah, set of edges. So a matching can only be perfect if the number of nodes, the number of vertices in the graph is even. Now, looking at maximum matching, meaning we're looking at the size. Now, notice here I use two different notions, maximal and maximum. Here in this particular case, they're different. Maximum means you're looking at only the size of the matching, whereas maximal means the matching can no longer be added a new edge without violating a matching. So it's maximal in the sense in a similar way as a maximal element. Yeah. So a matching is maximal if that matching cannot be or is not a proper subset of any other matching, or in other words, you cannot add another edge to the matching without violating the matching condition. Remember, matching is simply a set of pairs of nodes such that no edge share the same vertices. Right. Meanwhile, the notion of complete matching is a notion that is only relevant for bipartite graphs. So a matching is a complete from one partition to another. Yeah. An example. Yeah. Here, to maximum and maximal matchings. Now with that, now with this one, with this problem, this example, we look at the complete matching of bipartite graph, right? Yes, so there is an examples as well as exercises. Okay, any questions on this? No? If there's no questions, let me go to number 4, representation. So here's, I think I have the videos just to clarify. The definition I use here is a definition that also covers graph, covers parallel edges, covers loops, covers parallel edges and all, right? So for example, if the graph looks like this is an undirected graph, right? So if the graph, I think we have example here. So here in this case, the adjacency matrix would be, so yeah, let's have a look. So if it's a loop, this one, it's 2k. Yeah. What is k? K is the size of the edge. Sorry, 2, I should say 2 for each loop. Each loop is 2 and each edge non-loop is 1. So in this case, A to A, you have 2 here. And then A to B, we have 2 edges. So therefore, we have 2. A to A and C, we have 1. And then A and D is 0. B and A should be 2. Here should be B and B should be 0. B and C should be 0. B and D should be 2. And then C and A should be 1. C and B should be 0. And then C and C is 0. And C and D is 2. All right. So, and then here D and A is 0. Or let me just put it down here. D and D is 2, right? So that means 0, 0, 2, and 2, 2, and 2. Right? So if you sum the degrees, yeah, if you sum them all, this is 5, 4, 3, and 6. Yeah. So 1, 2, 3. Degree of A is 5. Degree of B is 4. Degree of C is 3, and degree of D is 6. Right? Yeah. This is degree of A, B, C, and D. Yeah. Now, what about directed graphs? Directed graphs is the similar, right? So in this case, we use adjacency matrix is simply the number of edges going out from I to J, right? So therefore, A, B, C, D, E, and F. A, B, C, D, E, and F. So A to A is 0, A to B is 1, A to, and that's it, right? Over B, you have, so if you look at this, yeah, it's the number of edges. So therefore, from B to C, nothing, but B to E, you have 2. So you have 2 here, but 0 less. Yeah. And then C, you have a loop. So C to A is 0, C to B is 1, C to C is 2. Now remember, a loop, the number of edges that, number of loops, not 2, should be 1. Yeah. Sum of the row is out degree, sum of the column is in degree. Yes. Okay. Yeah. So it's 1, not 2. So it's 1. C to D is 1. And then C to E is 0. C to F is 0. Well, F has to be 0, everything. So because F is not connected. Now D to A, it is also 0. D to B is also 0. D to C is 1. D to C is 1. D to D is 0. D to E is 0. Right. So E to A is 1. E to B is 0. E to C is 0. E to D 0. E to E is 1. So the sum of row, yeah, the sum of row is just 1, 2. Sum of row is this is the out degree, out, so out degree, and this is the in degree. So 2, 3, out degree of C is 3. 1, 2, 3. Yes. This is 1. Out degree of D, out degree of E is 2. Yes. Our degree of F is 0. Yeah. So what about the column? This is 1, 2, 2, 1, 1, 0. So that is for example, B in degree of B is 2, right? Because from C and from A. right? So that's how we fill out the adjacency. If you sum them all, the sum of out degree is the same as sum of in degree. So very good. All right, that would be adjacency matrix. What about incidence matrix? Incidence here for undirected graph, we use 2 if it's a loop, yeah, and 1 if it's not a loop, but incident at that node, right? Here, here's also a few examples. Again, here 2 is a loop, 1 and minus 1. If 1 is for the source and minus 1 for the target. All right, any question?
Sir,
Hmm?
I think in the previous adjacency matrix, sir,
Hmm.
I believe in that one, I believe there's a node from E to D, right, sir?
Do we have a node from E to D? Oh, yes. Sorry.
An edge, I mean, sir, sorry.
E to D and E to A. Yes. So the has to be 3. Something is wrong then. Oh, it should be 3. Oh, yeah, this is 3. This is 2. This is 2. This is 2. This is 1. 1, 2, 3, 3. Do I make mistake somewhere? Oh. Okay. And 1. B, 2 in, 2 out. 2 in, 2 out, yes. C, 3 out, 2 in. Yes. D, 1 out, 2 in. 1 out, 2 in, yes. E is 3 out and 3 in. Yes, so this is correct. So what will be the sums? 1, 2, 3, 1, 3, and 0. So this is 6 plus 4 is 10. Yes, and this is 1, 2, 2, and 2. It's 7 plus 3. So, yeah, so it's fine. Yeah. Okay. Thank you. Good. Another question? No? If not, then let me revisit the isomorphism. Here, hold on a second. I think I have a few examples. Here, so what is important is that for you to learn is isomorphism means that there has to be a mapping that follows the structure, right? As I explained earlier, if you cannot find that mapping, so then it is possible that you not. Then if you already try every possible way to try to create the mapping, then yes, that's not possible. Isomorphism. Yeah. If there is some isomorphism, you should be able to construct the mapping in the correct way, right? So here's an example, yeah, on this one. Here's the concept, right? So in an undirected graph, if you have u and phi and the edge between them e, then if you map u to u prime and phi must be mapped to phi prime, and then e must be mapped to e prime, the edge between u prime and phi prime. So they have to match the structure, right? Yeah, this is, I've shown this before. Yeah. Yeah. Okay. I think I gave you examples of this. Right, maybe you want to try this and then have a question on that, right? Um, and finally, for the connectivity, um, so from the beginning. So here's an example, a path. Yeah, so a path. So and the complete specification of path usually includes the edges as not just the vertices, right? So for example, uh, from E1 phi E2 W is a path. In this case, we call it a node simple path or a simple path because we don't have duplicate nodes and duplicate edges. Now here also we have from E1 phi and then E2 W E4 X E5 phi. Now by our definition, this is a simple path because there is no duplicate edge. There is no duplicate edge, but duplicate vertices are allowed. But there is no duplicate edge. Duplicate vertices are allowed, right? And not simple circuit, not simple circuit is a path, is a not simple path that goes back to the uh, the original vertices. So in this case, there there is duplicates. There are duplicates Z here. Yeah, Z7Y E8Z. It's a not simple circuit. Yeah. So that's some examples. A simple circuit, for example, here from Phi E2 E2 and then W E4 X E5 Phi E10 S E11 T E12 Phi. So it's a simple circuit, but not simple circuit, right? So that's a definition. Yeah. Here's an example. So strongly connectedness and weakly connectedness. So the first in undirected graphs here. So these are not connected. Here is connected because here in this case we have this graph together, right? Yeah. Here's I think you know this already. Now connected component is a subgraph of the original graph that is connected and maximal. So connected and maximal. See, we call it connected component, meaning that you cannot enlarge the component without violating the connectedness. That would be connected component. Yeah. So here's an example. Connected components would be, well, this is one graph, right? And this graph has two connected components, namely this one and this one. Yeah. All right. Now for undirected graph, you can have strongly connected components Yeah. For example, so this is one. Yeah. And then this is one. And this is one. So you see that? You see the connected components? Because in each of the connected components, every pairs of nodes are connected. Every pairs of different nodes are connected. Yeah. Every pairs of different nodes are connected. Are strongly connected, I should say. Yeah. Next question? No? So I did not discuss this. I think, I don't know, but maybe there is there has to be a discussion on the videos. But if it's not part of that, then it will not be part of the exam. But there should be an, an video, so right. All right. So with that, let me finish this with path here. Path of length of path is wow. In Rosen, there is a discussion on how to count how many paths of length 3, for example, from B to E. Well, this is done by performing exponentiation to the adjacency matrix. Yeah. All right. Good. Any question at the end here? No? Well, if there's no question, so let me conclude the session today with a recap. So what we discussed is up to connectivity. The exercises should help you in discussing that. But for next week, we will recap connectivity again and then discuss two important notions in graph, namely Eulerian circuit and Hamiltonian circuit and path, right? So with that, let me conclude the session and thank you. I'll see you again next week.